The diagram shown here is a more realistic representation of diffraction. For polycrystalline samples, there are small regions called grains in which all unit cells are aligned in the same way. These grains are outlined in red in the figure, and neighboring grains have unit cells that are oriented differently. Let's pretend that the lines within the grains shown here correspond to the 100 plane, and that the X-ray source and detector are at the proper angles for constructive interference to occur for the 100 planes, normally producing a peak in the diffraction pattern. The diffraction vector shown here is the vector that bisects the angle between the X-ray source and detector. In this example, the diffraction vector points straight up and is perpendicular to the diffraction plane. Here are the normals for the 100 planes for each grain. The only grains that will contribute to the appearance of the diffraction peak are those whose normals align with the diffraction vector. In other words, this grain is the only grain shown here that will contribute to the diffraction peak. Now let's look at a sample with preferred orientation. In this example, our diffraction vector is the same as before, but the 100 plane normals are different. For this sample, there is a clear preference for the 100 normals to point up and to the left. Because none of the normals are aligned with the diffraction vector, no grains will contribute to the diffraction peak, so only background will be visible for this atomic plane, even though the source and detector are at angles that should produce a diffraction peak. When we collect pole figures, we align the source and detector at angles such that diffraction from a certain plane should occur. We then rotate the sample around two axes to determine qualitatively how many grains are aligned with the diffraction vector at each position. Let's go ahead and look at a real-life example. On the right, we see the setup for collecting pole figures. Here is our sample, a square piece of cold-rolled copper. X-rays strike the sample from this direction and diffract off in this direction to be picked up by the detector off-screen. The system has been set up so that the source and detector are positioned such that the 111 reflection should be detected. Once the measurement begins, the first thing that will happen is that the sample will rotate 360 degrees in phi, which will be represented as the appearance of data in a similar fashion on the left. The sample will then rotate back into the screen in chi, which will be represented as a movement away from the origin in the pole figure. As I said, we first rotate along phi and we see almost no intensity on the plot, indicating that there aren't any 111 planes oriented correctly for diffraction. We then rotated a bit back in chi, then rotated in phi again while collecting data. This time we start to see some intensity appear, so some 111 planes are oriented correctly. As we continue to rotate further in chi, more intensity is seen at certain parts of the plot. We continue this until chi reaches approximately 70 to 80 degrees, because it is at this point that the X-ray beam typically begins to fall off of the sample. Because this type of experiment deals strictly with the intensity of the peak, the entire X-ray beam must remain on the sample throughout the experiment. We see that at certain orientations the intensity is much stronger. This tells us how the 111 planes are preferentially oriented in our sample.